Well, welcome back, everyone. Formerly, we looked at the tectonic forces that built the mighty mountain up. Now we need to take a look at the gradational processes which wear the mighty mountain down. Well, what wears down the mighty mountain? It's the cumulative effect of raindrops, usually. We'll, in this section, talk about weathering. Weathering means that the rock combines with the weather in some way and gets weaker. Mass movement, formerly known as mass wasting. Your textbook calls it mass movement. So that basically means gravity, slumping down, landslides type of thing. And then erosion taketh away. Regarding the weathering of landscapes, let's have a little bit of questions and answers about which of these are examples of mechanical or physical weathering and which ones are examples of chemical weathering. And you'll need to explain why. All right, let's take a look at these. Anybody want to know? How about oxidation? Is oxidation mechanical or physical weathering, or is it chemical weathering? Oxidation. Any answers? Well, that means combining with oxygen. Iron in rocks combines with oxygen and makes ferrous oxides, which are a weaker form of the rock. Now you've seen iron oxide before. That's rust. All right, when iron things are exposed to the air, eventually they may combine with oxygen in the air, and they start to rust. Well, the rust is a weaker form, and it's more quickly eroded away. How about freeze-thaw action? Is that chemical or physical? Freeze-thaw action would be a physical type of weathering. What freeze-thaw is that's when water gets in the cracks of rocks, and then the temperature goes below freezing, and the water freezes into ice, and the ice actually makes a little bit of force against the rock and expands the crack a little bit. And then, say the next day, or whenever the ice melts, it goes down by gravity further into the crack, and then when it freezes again, that ice, which the ice is a lower density than liquid water, it takes up more room. So when the ice expands, it opens the crack up a little bit. And then when that ice melts, the water goes down further into the crack and so forth. So as a repetition of freeze-thaw action, the cracks get wider. So what you're doing there, you're not chemically changing the rock, as with oxidation. You're fracturing the rock. That's a mechanical or physical process. How about plant root action? Is that mechanical or physical? Well, with the plant roots, it's classified more of a mechanical or physical weathering. Because kind of like the ice that can get in and crack rocks, plant roots get into cracks in rocks, and as the plant grows, it cracks the rock open a little bit more. So again, you're not chemically changing the rock, you're just fracturing it to a smaller form. What's hydrolysis? Hydrolysis is a chemical type of weathering, and that's when the rock chemically combines with water in some way and makes a weaker form. Okay, next question. How about salt crystal growth? Now, you're dealing with the growth of crystals, and maybe you did that in chemistry class. And so you're thinking, well, that has to be chemical weathering, right? But the salt crystal growth is classified as mechanical or physical weathering. In that, and especially in arid land areas where there's a lot of evaporation, even rainwater has a little bit of dissolved salts in it. And those salts build up in the cracks of the rock, and they grow and get bigger, and they further crack the rock open. How about carbonation? Is that physical or chemical? Oh, carbonation is chemical weathering. Let's see, how can we talk about carbonation? Well, if you know how Alka-Seltzer works, or you put it in the glass and it dissolves, it fizzes, can you put a rock in a glass of water and have it melt or dissolve? Well, it's not going to right away, but rocks that are rich in calcium carbonate, your limestone rocks, will over time dissolve naturally through the rainwater that percolates down through the bedrock, sometimes opening up and eroding caverns. And we'll take a look at this carbonation process when we look at what's known as karst landscapes. How about mass movement or mass wasting? Mass wasting sounds more exciting. Hey, it was a lot of wasting. They got wasted. Well, all that means is basically gravity, in that once the rock is weakened through weathering, and it's crumbled up, well, then it just eventually it falls down by gravity. So a big pile of rocks at the base of the slope. There's a technical term for that. Who knows? You might see that term on the test. That's called talus, and here you have these talus slopes. Well, the rocks just rolled downhill. All right. Well, also landslides. That's also an example of mass movement. There, when soil and rock are weakened, and especially after rains, the land will turn liquid and just by gravity action slump down slope. Even soil on hill slopes, if they're especially moist, they will also fall downhill, although very, very slowly. That's the reason why it's soil creep. But over time, is what you can see here, these trees are creeping downhill, although very, very slowly. Well, that's not as fast as a landslide, but it's still an example of mass movement. So talus slopes, talus cones are a landform feature. It kind of looks like it makes a cone at the base of the slope. All right, look for that. Right, mass wasting means landslides and slumps, which cause a lot of economic damage every year. How about erosion? Well, once rock is weathered and once it falls down, then erosion will taketh away. It will pick up that loose rock and move it somewhere else. Now sometimes, we talk about the erosional cycle. We talk about weathering, mass wasting, and erosion all together. And sometimes I cheat and I say, well, it's eroded. But erosion is actually when the rock materials are picked up and removed. Now, there's a big difference between the natural erosion that goes on to wear the mighty mountain down over millions of years versus the accelerated erosion that human beings get involved in. And a good example of that is this field where when you plow the field too much and you don't have cover crops and and other processes that don't conserve that would conserve the soil. Well, when it rains, then you're going to have runoff, and the water is going to run off with your soil, creating these gullies. And once these gullies start, the gullies just get bigger and bigger, and that field there, it may erode back, and there's not going to be any soil left anymore through this gullying. Once a little gully gets started, it gets bigger and it gets bigger and it washes away the topsoil. So the farmers here better be careful, and they better be setting up a system that'll try to conserve what soil they have left. So this would be accelerated erosion when human beings get involved with that. That's different than the natural erosion that takes a long time. But still, landforms are sculpted by the erosional agents. Well, running water is the major erosional agent. Okay, most landforms are sculpted by water in some way. And that question, how do rivers shape landforms? That's a very involved question. I mean, that's what a lot of geomorphology studies. That's almost like asking, what's in the Encyclopedia Britannica? Well, there's a lot. There's a lot of ways. So this is a long story. We'll take a look at the basics. And what's alluvium? Not aluminum, but alluvium. What's that? That's a term. What's a floodplain? And the so what part of it? Well, how are alluvial floodplains important for humanity? They've certainly been historically important. But let's take a look at a few ways in which rivers work. Here's a satellite view of the Ganges and Brahmaputra rivers in India and Bangladesh, which those rivers are fed by the streams up in the Himalayas. And basically, what Bangladesh is, it's a big delta. It's a big delta. It's all those sediments that are washed down from the Himalayas. They're carried by the rivers downhill, and they settle with the river slower where it meets the sea and forms a delta. And over time, basically, the country of Bangladesh is sitting on one big delta. All right, let's see. So what are the rules for how rivers work? Well, let's see. Some basics. Well, water always runs downhill. Okay, I don't think you'll find any exception to that. So that's easy to see. And also, water running downhill, it always takes the path of least resistance. It might not be a straight line to go from uphill to downhill. There may be some meanders, but in all cases, the water is always going downhill. As a side note, it's sometimes said that rivers are crooked for the same reason people are crooked, or is it the other way around? People can be crooked the same reason that rivers are crooked, because they take the path of least resistance. All right, well, here's how it works. At the higher elevation, and here we have a cross section, you have the river. It's cutting a V shape into the upland areas. And then as the river water flows downhill, it's at a lower elevation. It's not going as fast. It doesn't have enough force to downcut as much. So it starts to spread out and meander a little bit. It's eroding in some places and it's depositing in other places. Till finally, when you get down to the lowest elevation, near the mouth of the river, you have deposition takes over. You still have some erosion back and forth, but now all of that material from the headlands is being deposited near the mouth of the river, and the river is flowing slower. See, when the river is moving fast, when it's up here, it means that it can go fast. Water can go fast. It can do a lot of down cutting. It can carry larger rocks. But when it's down here where the river is slowing down, well, it doesn't down cut very much, and it can't carry larger size rock particles or sediment particles. All right, so when a river flows fast, it erodes. When a river slows down, it deposits its load. Now, there's a question in the quiz bank, test bank. Who knows? You might see it on the next quiz or the final. All right, and I thought it was a pretty good question. What is the relationship between moving water and its load? Let's see, is it slow moving water has no stream load? No, there's going to be some. Rapidly moving water has a lesser stream load? No, it works the opposite. Rapidly moving water has a greater stream load. That's the true one. And then the other, slow moving water is a greater stream load. The answer here is C. Rapidly moving water can pick up and carry a greater stream load. Where it slows down and it can't hold those larger particles, it'll drop them. And the smaller and smaller particles are carried by the slower moving water. Okay, you can think of muddy river water. Is that river carrying rocks? Well, the mud is little bits of sediment, little particles that are giving the muddy river water its color. Technically, you won't think of it as being rocks, but they're still carrying sediment, though. Okay, so you have larger size particles the faster the water is moving. Okay, is there anything else here that we need to take a look at? So here in the upper reaches, you have more down cutting, and as you get towards the lower river, they start to meander. You have less down cutting erosion, more lateral erosion with the meanders, and then finally in the lower courses more deposition. All right, now let's see, downstream floodplain formation, oxbow lakes and stream meanders. So where you're down here in the lower courses, the lower reaches, the river water is going slowly, but it's meandering back and forth. See, it's not down cutting very much. And river water, it's always taking the path of least resistance, and sometimes it'll cut a new channel, and you'll get an old branch that's been cut off. And so these are called oxbow meanders, oxbow lakes, because it looks like the bow that a farmer might put on his ox, put over the neck of an ox. It's an oxbow. All right, so there's a question in your quiz bank, at least you might pull it, in that if you see an oxbow lake, you know what? Well, you know that a floodplain has been formed. Okay, and here's a depiction of all the textbook features of what's in a floodplain. All right, here we have a picture of the Missouri and Platte River floodplain. At one point, flowing within their banks, and then the other one during its flood stage. So it's kind of good to compare and contrast. Here, that's where it's usually contained there. But you know what? If you live in a floodplain, there's a reason why they call it a floodplain. it floods. All right, this is more of a special topic. It's probably beyond Geography 1010, but perhaps if you take earth science or perhaps even geomorphology someday, you may encounter entrenched meanders. You might be thinking, well, hey, wait a second. On steep slopes like this, wouldn't the river, downcut a V? You wouldn't have meandering in this case. Meanderings for floodplains, not for these canyon lands like this. Well, let me tell you what's going on here. You see all these meanders. Well, at one time, there was a floodplain formed there. The river was going through. But then there was a period of uplift. The whole landscape was raised up. And so the river course, well, the water was at a higher elevation. The river was at a higher elevation. So the downhill gradient was a lot greater. And so it started to downcut again. And so that the meanders are in place, it started downcutting again. So what these are entrenched meanders. Landscape is still going up, but the river, even though it's a meander, and that represents a floodplain, it's entrenched. And so it will continue to cut down as long as there's uplift here. That one's kind of unique. Also quite beautiful, too. Let's see. All right, where the river meets the ocean, the gradient is the lowest, the speed of the river is the slowest, and it just dumps all of its load at that point, at the mouth of the river. Now, such alluvial features are called deltas because very often they take the shape of the Greek letter delta and other forms too. For example, this is the Bird's Foot Delta of the Mississippi River. See down here, there's New Orleans, and here's the Bird's Foot. Why does it look? Why is it called a bird's foot? Well, it kind of looks like bird's foot, with its talons and claws here. It does kind of look like a chicken foot delta or bird's foot delta. See where the river is meeting the ocean, slow gradients. Sometimes some of it goes in this direction, sometimes some of it goes in that direction, where it deposits load and builds up land, and then it's got to go through again, seek the path of least resistance, go a different way, and so it builds up this characteristic landform. It's called a bird's foot delta, sometimes a chicken foot's delta, which I think is appropriate because, down in New Orleans, Louisiana, some people, they actually eat chicken's feet. All right, so the more classic delta shape might be the Nile River delta, and it kind of looks like a triangle, like a delta. All right, now here, this is a special topic for those of you that are going to be teachers. Right, you may be teaching in K-12 geography, the difference between, or in history, Lower Egypt and Upper Egypt. Why is it that Upper Egypt is down here and Lower Egypt is up here? Well, you remember you're looking down on a map, and the river is flowing on the path of least resistance. It's going north. Can you have a north-flowing river? Sometimes kids have a hard time understanding that point, because you're holding north as up, and you always say, well, rivers can't flow up. Well, right, rivers can't flow uphill, but they can certainly flow north if that's where the downhill is. And so here you have the Nile River and its delta. So the area known as Lower Egypt is lower because it's lower elevation. Once again with alluvium, when we When we say alluvium, we mean all the silts and sediments that are carried by the running water. Sometimes, and especially in arid landscapes, you have it doesn't rain very often in arid landscapes, and some of the rivers and streams will be a little bit more intermittent or ephemeral, and they don't carry it too far. Just basically it's depositing it at the base of the slope, and they're fanning out, and so such features are called alluvial fans, built up by these silts and sediments that we call alluvium. Now, alluvian and alluvial floodplains are very important in world history, as we may see in Chapter 6 in Cultural Geography. Where were the world's first civilizations originating from? Well, it depends on how you want to define civilization. When people were living in the first cities, how far do we go back with that? Well, that's this area in the Middle East called Mesopotamia, the Middle River area, the Tigris and Euphrates River, which is in present-day Iraq. Well, that area was the beginning of civilization, where people figured out irrigated agriculture, rivers flowed down, there were fertile areas. People figured out if you put the early wheat plant in, you'd get more of that, and then built the first cities. And then the Egyptians also, their culture was based upon the alluvial floodplains of the Nile River. So the two earliest civilizations are alluvial floodplain civilization. Well, how about India? All right, in India, the base of its civilization is the Indus River Valley. And so that valley, a fertile area, alluvial floodplains, good for growing crops and supporting a large population. Well, how about Chinese civilization? What's the basis of Chinese civilization? Well, could it be, did it arise in an alluvial floodplain area? Indeed, the confluence of the Huanghe and Wei rivers, an alluvial floodplain, good for agriculture, could support a large population. In Southeast Asia, the Mekong River Delta. And so you see that the world's oldest civilizations are based on river valley floodplains. So it's an important topic, and it has some importance for humanity. All right, next up, we're going to take a look at the difference between arid land erosion versus erosion in more well-watered areas in human landscapes. We'll take another break at this point.